Okay, guys, so this is the final part of the 2022 software exam. This is the interrelationship between software and hardware. So the first part of this is show how two different integers can be represented by the binary number shown here. Now, the way you understand this is the two representations would be um, uh, basically how you represent um, numbers can be shown in two different ways. So the way would be like basically having a sign bit. That would be one way, where the idea is the leftmost bit represents the sign. So by sign, I mean either plus or minus. So in this case, if we were to treat this number with a sign bit, where the 1 is a negative, so therefore we would extract the right bits. So 0, all those zeros, 1, 1 would just be 3 in binary, right? Because obviously you've got 2 to the 0 plus 2 to the 1, which happens to be 3. So in this case, this could be representing negative 3. So that is one way. The other way would be to basically this is you could represent it using 2's complement. Now, if you remember this, it is the strategy is to do 2's complement. We want to flip all the bits, and then we add 1 to it, and then we have the number. So in this case, it would be 0, 1, 2, 3, 4, 5, 4, 5, 0, 0, and then obviously we wouldn't add a 0 there, we'd add a 1. And then you'd say, okay, what does this number equal? This number equals 2 to the 0 plus 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, which is 1 plus 4 plus 8 plus 16 plus 32 plus 64, which we don't have a calculator in the exam, so you have to do this manually. So 3 plus 4 is 7, 7 plus 8 is 15, 15 plus 16 is 31, 31 plus 32 is 63, 63 plus 64 is actually, let me double check this. Okay, wait, so let's go backwards. 64 plus 32 is 96. 96 plus 16 is so 112. 112 plus 8 is 120. Wait, there should be 100 and yeah, the 4 plus the 1, my mistake. So there was no 2, so therefore it's 125. Okay, so that would be minus 125. So if that was a negative number, we're using 2's complement, it would be negative 125. So see how there's two differences. So yeah. Okay, so show how to calculate 32-bit IEEE 754 single precision floating point number that represents the decimal fraction minus 1 over 32. The first step is done for you. So basically there's a few steps here. So the steps to converting this to so basically it's just going to be one big binary number. And the binary number is going to have it's going to have 3 parts, which is the sign, the exponent, and the mantissa. So we're basically going to take this, and it's how we can represent a decimal, a decimal number with a a point, a decimal fraction in binary. So the steps we're going to do is first you take the decimal, and we're going to do normalization. So, which basically means we want to bring the 1 to, so it's going to be like 1 times 10 to the something, or in this case, not 10, it's going to be base 2. So whenever we say the word normalize, it's basically bringing it back to the base. So usually when you do this in maths, you bring it to like 1 times 10. But in this case, since we're dealing with binary, it's going to be base 2. So what we do is we're going to write, it's going to be, if we represent this, if we normalize it, it's going to be -1 times 2 to the 5. Okay. 2 to the -5, sorry. Not 2 to the 5. Because we're bringing that 1 on the rightmost part left, so therefore it's -5. So it's like whoosh. Yeah. So then what we have to do is we have to, so another, as part of this 754 single precision floating point, in order to convert it, you need to do this step called adding 127 to the exponent. So yeah, so all we need to do is add 127 to this -5. Obviously, what we're going to get is -1 times 2 to the power of 122. Okay. Then what we have to do is we can convert this exponent, which is 122, into binary, which is it's going to be, so how we do this, how we convert from, let's say we have 122, and we 122 in decimal, we want to convert to binary. What we do is think about the powers of base 2 and find the largest base 2 that can fit into it. So instantly I know 128 can't fit into it. So the next base would be 64. So I take the 64, right? Take the 64 and subtract. So I'm also going to write a 1 down here, which represents the 64. So we're going to subtract. So 2 to 4, you take a 1 there, 12. And we're left with 8. Take 1 from there. Got 11. So 11 minus 6 is 5. So 58. Then we think about what's the next thing we can take. 32. We want to subtract 32, which is another 1. So this would be 6. Be 26. Then we can take 16. That'd be another 1. So 0, 1. Now, can we take 8? Yes, we can. So we're going to be left with 2. So can we take a 4? No, we can't. Can we take a 2? Yes. Can we take a 1? No, because we're out. So the representation would be 4 1s, 0 1 0. So we could write it now as -1 times 2 to the binary of 1 1 1 1 0 1 0, which is just 1 2 2. Okay. So then now obviously with the exponent is 8 bits, so we'll add a 0 at the front here, because we don't want to add a 0 to the right, because then that will change the number, so we just add a 0 there. So then what we want to do is write out the actually write out the the actual representation. So obviously how we do this is, I'll just clear some space up the top here. So we're going to have a sine, we're going to have the exponent, and then we're going to have the mantissa. So when we write this, the sine is obviously 1, the exponent's going to be 0, 1, 1, 1, 1, 0, 1, 0. And the mantissa is going to be then 32 zeros. Actually, no. It's going to be, no, my mistake. It's going to be so 32 bits. So 1 is the sine bit, 8 are going to be the exponent. Therefore, there's going to be 23 bits for the mantissa, and all those are going to be 0. So just have to draw a bunch of zeros. So that's 8. So just draw you just draw a bunch of zeros. So that's how you represent the and so that is the answer. So yep. All right, so moving on. Write a Boolean representation for the following logic circuit. So basically, you might need some working paper for this. The easiest way to understand is probably just to do a truth table, right? So we'll go ahead and go A, B, C, A, B, C, and then we'll write out the output. Actually, we might need to create some space, so I'll just go A, B, C, and then out. Right, so the basic idea is to do this, you go through all the different combinations of the ABC inputs. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. And then 1, 1, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So then we basically have to determine what the output is. So if they're all off, and so the reason we have to do this is because the Boolean representation is basically just you write for what inputs would you get a 1 for the output, right? So that's what we need to figure out. So if everything is off, so this would definitely be 0. This is 0 because it's an AND. So this is an AND gate, by the way. So the idea is both inputs need to be on for it to produce a 1 output. And this is called a buffer or a not buffer, where it or you could call it an inverter, where basically it inverts the signal. So if you input a 0, you output a 1, and so forth. So this looks like it's 0 as well. So in this case, we're at 0. So if C is on, I can already tell that it's not going to work. So we'll just put 0. If B is on, but nothing else, that will also not work. If B and C are on, so that would be 0. That would be 0 there. So that would also not work. If A is on, then So this would be 1 and this would be 1, so this would be 1. So you would get a 1. So if just A, so wait, let me double check this. So A so this wouldn't fire. Yes, that should be a 1. If A and C are on, but not B, that should also be a 1. If A and B, but not C, then I can tell that this will be firing, so that should be a 1. And if all 3, then that should be a 1. So in this case, it should be A not B C plus A not B C plus A B not C plus A B C. So there should be a way we can see if we can simplify this. So so then we can do so basically we can look at this and say, well, we can say A not B C plus not C, right? Because I've just made an equivalent statement. And then we can also say now C plus not C is just nothing, so we can just literally ignore that. And then we can say or actually just leave that. And we can say plus AB C plus not C. So I've just extracted that. Then we can divide both sides. Then we can extract that even further and say like so then we can do like A not B C plus C, not C, plus B, C plus not C. I think there's a better way to simplify this. Oh yeah, so I was on the right track. I just checked. So basically, C and not C cancel out, obviously, and then you just extract the A, and then it's B not B, so you're left with A. And then you look at the truth table, obviously, and you can see the only time the output changes is dependent upon the A. So if A is 0, the output is 0. If A is 1, the output is 1. So um, yeah, right. A logic circuit is needed to determine whether to hold an outdoor event based on current conditions. The truth table, the characteristics of the circuit. Design a logic circuit to meet the following requirements. So basically we need to translate this into some sort of truth table and then do it into a logic gate. Okay, so these are the inputs. So you're gonna have like D, C, and R are going to be inputs. The event can be held at any time if it's not raining. Okay, so basically, if it's raining, it's off, right? So you're going to have like some sort of uh, so I would say like I would just do something like this instantly. So you can have a negative buffer. So if it is raining, so if it's not raining, then you want to activate this AND gate, and the other part of this AND gate is going to be based off um, uh, the D and the T. So we'll just go like this, just give some space, and then do the AND. And now we're going to say, okay, now we look at the D and the T. The event can also be held at night if the temperature is above 21 degrees, even if it was raining. Oh, okay. All right, so you can't do that. So there's a condition where if it's not, so there's special conditions if it's night, right? So if it's not raining, the event can be held day or night. But if it's at night, so only in the condition that it's night. So if it's raining during the day, you can't do it. But if it's nighttime and it's above 21 degrees, then there's a special condition where you can allow it to happen if it's raining. So so basically we have to think about all that matters is it raining? If it's raining, it's off, except for this particular condition. So we need to map that out. Okay, so basically, there should be a direct, we're going to have an or, okay? And there should be a direct buffer, which says an opposite buffer or an inverter. So basically, which basically says if the input is 0, then we output 1, which means the event can be held. So if it's not raining, no matter what, event's held. Now, the scenario that we have to look out for is if it is 1, then we need to play around with the D and the T, right? So the only time where if it is raining, can we output a 1 for the event to be held is we need to think about the temperature has to be, the temperature has to be above 21 and it has to be night. Therefore, D needs to be 0 and T needs to be 1. So D needs to be 0. So we're going to do an AND gate here. So D needs to be 0. So we'll do an inverter. It needs to be 0. And temperature needs to be 1. That, and then we do like that, and boom, right? So the idea is and then we also need so actually when it says even if it is raining, so we don't really care if it's not raining, right? If it's not raining, then no matter what, we're good, right? It's only in the scenario where it is raining that therefore the event can be held if it's night and it's over 21 degrees. So this should capture all those scenarios. So for example, if it's night, so 0, therefore it's, I'll do a different color. So if this is 0, this is 1, and this is 1, therefore this will be 0. So that we don't know if the event can be held. If it's night, therefore this will be 1. And if its temperature is 1, which means above 21 degrees, this will be 1. So that's an AND, therefore that'll be 1. Therefore it will be a 1. So there you go. So if you need to, you can also do a Boolean algebra or a truth table, but in this case, you can just try and figure out which gates will work in this scenario, right? Generally, I try to find the output that's the easiest to understand. So basically, this was like an easy, like, okay, the only thing that matters whether the event will run is if it's raining. If it's not raining, it's always going to be a 1 no matter what. And then there's the scenario where, okay, if it is raining, there's a special scenario where it can still be held. So, yeah. Okay, so now we're going on to basically the bit stream question, which is universal among all the past paper exams in this option topic. So we're going to go over it. So a basic robot vacuum cleaner can move across the floor of a rectangular shaped room, vacuuming as it goes. So it's like a Roomba. The cleaner is circular, 4 sensors, blah, blah, blah. The controller sends and receives the data to and from the cleaner. Looking down part of the room, it should appear as shown. Direction of movement. Cleaner is currently at 3.5. Data stream from controller to the cleaner. The data stream instructs the cleaner to either move to the specified coordinates or change direction and move 1 square. So it's a 16-bit data stream, depends on the move, is specified in the first bit, type of move. Okay, so it specifies the coordinates or it specifies the direction to move 1. Okay. what are the following data stream achieve? Okay, um, so basically you just have to understand the data streams. Obviously, we'll start with the first one. So basically it's going to be a move. So we're going to move to the coordinates 2, 3, 1, 2, 3, 4. 1, 2, 3, 4. So we're going to move to the x, that's the x coordinate, and that's the y coordinate. So we're going to move to position, what is it? 1, 2, 4, 8, 16, 32, 64. Does it say? Okay, so it's a big, big place. Okay, so this would be 4, 32 plus 64, 96 plus 4. So 100. We're going to move to x coordinate 100, and y is going to be, so 100, and y coordinate 40. So yeah, so that's going to be the first step, and the last bit's unused, so it's going to be x. This is going to go to position 140. And the next step, it's going to it's not going to move to a coordinate system. It's going to just simply change direction 90 degrees anti-clockwise. So it's going to be going this way, and it's going to move 1 square. So that means it's going to be at position where does it start? So I assume it means it's pointing down. So it's going to basically start looking right and move 1 across. So that would be 40, it'd be at 41. And then it's going to be 0, 0, 0. So it's just going to be position 42, right? Because it's not going to change direction. Well, actually, we don't know what direction, but it's just going to move to that position and then move anti-clockwise and then 1, 1. So, yeah, so 100, 100 and then 40, and then it's going to go anti-clockwise, move 1, and then move 1 again. Data stream from cleaner to controller. As a cleaner is data stream back to controller, the cleaner also indicates when the battery needs to be recharged. The data stream has the following format: X, Y, battery, sensor. The sensor bit can be 0. Create the data stream from the cleaner to the controller. So in order to do this, that's pretty straightforward. We need to convert 42 and 18 into binary. And nothing sensed, so the last bit's going to be 0, and the needs charging is going to be 1. So we just need to convert those two. So 42. So first off, the biggest one is probably 32, right? So we subtract that, so we're going to get 10. So it's going to be 1. Then 16 doesn't fit, so that's going to be 0. 8 fits, so that's going to be 1, left with 2. 4 doesn't fit to, yeah, so it's going to be 0, 1, 0, 1, 0, 1, 0, which is 42. And then we're going to do 18. So we're going to do 18, so it'd be 16. It's going to be 1, and we're left with a 2, so 8 doesn't fit. 4 doesn't fit, 1 fits, 0, so it's going to be 0, 1, 0, so 4, 0, 0. So it's going to be, this is going to be the X, this is going to be the Y, and then you have 0, 1. So the total stream would be, we'll just type it, be 0, 1, 0, 1, 0, 1, 0, 1. Sorry, 0, 1. It'd be that, and then it'd be 0, 0, 1, 0, 0, 1, 0, and then it'd be 0, 1. So that would be the entire stream. So, yep. So pretty straightforward, no tricky bits here. Controller is located at 50 and contains a battery charger. A module called check battery is required to enable the following. The controller determines if the cleaner has a low battery by design the required algorithm for check battery. Okay, so this is kind of an annoying, difficult question. Basically, you need to construct an algorithm to do some functionality here. So controller determines the cleaner has a low battery by checking the data stream sent by the cleaner. Okay, so begin, check battery. First off, we know that the low battery I think is the second last bit. No, it's the last bit. So basically, in this case, we can just say something abstract like, just say get stream from cleaner. And then we need to basically say, we need to extract that last bit. So you just say, like status equals extract. So they give us a function, a helper function to extract the bits. So you put in the first parameter is the stream, and then the start bit would be the what did we say? It's how long is it? 14, 16 bit. So we need the 16th bit. So we need to say the start bit is going to be the 16th bit, assuming you're starting from 1, and you're going to extract 1 bit. Okay. So then you say if status equals 1, then so if it's 0, then we don't need to, it's not low battery, then we can end, we're done. So only in the scenario where it is a low battery, then when you send a data stream to recall the cleaner back to the controller. So we need to basically, first we need to construct we need to know what stream we need to send. So if we scroll back up, so the controller is there, and we need to send it to position 50. So the stream is going to be 0. It's going to be, no, sorry, it's going to be 1 because it's going to be positional move. So the type of move is going to be 1. The x coordinate is going to be 5. So it's going to be 0, 0. So 3 zeros, 4 zeros, 1, 0, 1. So that'd be 5. That's 5 in binary, and then we're going to put in 0, such as 0. So 7 zeros, 1, 2, 3, 4, 5, 6, 7, and then 0. That's going to be our string. So what we're going to say is, send to the cleaner. As I said, you can use these kind of fuzzy words because they don't really tell us how it transmits the code. So you can use like fuzzy, like plain English. Then as the cleaner moves back, continues. If the cleaner centers indicates an object in its path, so we're going to keep getting instructions. So what happens if it gets stuck? You do change direction. Oh, so we need to say if it's sensed something in its path. So we need to extract the 15th bit from the sensor stream. So basically we need to say, so get stream from cleaner again. And then we can say, like, I don't know, object sense. And we'll say it is, so we're going to extract the 15th bit this time. So extract from the stream, 15th, I'm just going to extract 1 bit. And I'm going to say, while there's no object, so while object sense is 0, get stream from the cleaner, object sense equals extract. We're just going to keep extracting the 15th bit until we find the point where it senses something. So if we do sense something, whether it's an object or whether it's like we end up finding the back to base station or whatever, send instruction to change 90 degrees clockwise and move 1 square. So it's just going to be so it's going to be 1 0. So it's going to be 0 1 0 and then 1 2 3 4 5 6 7 8 9 10 11 12 13. It's going to be that. So we're going to send that to the Roomba. So I'm going to say send that to cleaner. And then we need to say so we'll see so basically we need to think about what the object was detected. So if the object was something like a couch or something, then like obviously we need to redo the reset the thing so it like goes back to the coordinates we said, which was like 5 0. But if the thing it detects is actually the base station, then we need to know if it was the base station. So we need to say x equal, we're going to extract the coordinates and determine if it was the base station. So x equals extract. Also, first we're going to say get stream from cleaner. Maybe we don't have to do that. We just literally say x equals extract stream, and we'll say one. I'm going to say 7. I'm going to say y equals extract stream. I'm going to start at position 8 and go 7. And now I realize we need to wrap this in a loop. So we'll just say repeat until x equals 5 and y equals 0. So you should keep repeating that. And that should be it. So basically keep going to you basically have to keep extracting the bits from the stream. And if you find it, then good, then it's all good. And if you don't, so basically you extract the status of the battery. And if it's low battery, then you send it back to the coordinates of the base station, which is 5 0. If you encounter an object, then basically rotate 90 degrees and move 1 step. And if the scenario is that the thing that you detect, the cleaner detected is the base station, which is 5 0, then we finished. So cool. All right, so that's pretty easy. So like these questions are pretty difficult and confusing, but they're actually very straightforward. It's just like very easy marks, but most students can get intimidated. To be honest, I feel like I think it's pretty straightforward. So Cool, and that is the end of the exam. So we will leave it there.